Hey everybody. Today we're doing volumes of solids of revolution using the disk method. So a solid of revolution is just one that you get when you rotate some sort of two-dimensional shape in the coordinate plane around a fixed line. It's easiest to discuss this when we have a specific example. So let's get one. Find the volume of the solid generated when the region between y equals 4 minus x squared and the x-axis is rotated about the x-axis. So let's get a picture of the region and try to imagine what this is going to look like when we rotate it around the x-axis. Can you do that? Let's have a picture of what it looks like. There it is. It's going to have a vaguely football type shape. The way that we're going to find the volume of something like this is, of course, using slabs. We're going to slice this into thin slices. They're all going to be parallel to the y-axis. We're going to approximate the volume of each one of those slabs, and then we're going to use the definite integral to add up all those little bits of volume. So our general formula for the volume of a slab is a of x times dx, the cross-sectional area of a slab times its thickness. And in this case, each of the slabs is going to be a circle. The radius of the circle is going to be the height of the parabola, so pi y squared dx. The problem here, of course, we can't integrate until we get out the y and get the x's in. We're going to use the equation of the parabola to do that. It's y equals 4 minus x squared. We're going to substitute that in for that into that formula for dv, like so. We're going to need to integrate that over the entire range of values where we actually have slabs. So from x equals -2 to x equals +2. So here's the thing that we're trying to evaluate. The integral from -2 to 2 pi times 4 minus x squared dx. One little trick here. I'm going to integrate from 0 to 2, get that volume, and then double it. So find the volume of half of this thing, and then multiply it by 2. This is going to make the integration just a tiny little bit easier when we go to evaluate the limits. In order to evaluate this integral, I'm going to FOIL out the squared parentheses to get 16 minus 8x squared plus x to the 4th inside the integral. And then we're going to anti-differentiate for each term in that polynomial. I raise the power by 1 and then divide by the new power. Plug in the limits of integration. Simplify a tiny bit to get 512 pi over 15, about 107.2. Let's talk about this in slightly more general terms. So we can have kind of any function, y equals f of x, that's above the x-axis on some interval a comma b. Whatever that graph might be, we can rotate it around the x-axis to get a solid of revolution. I think it's helpful to draw in a rectangle before we do the rotation. Then when we are imagining the solid, we can also imagine one of the disks, like so. After doing a few of these problems, by the way, you get pretty good at drawing pictures like this. Next, we recognize that the volume of that disk is always going to be pi times the radius squared times dx, and that the radius is always going to be the value of the function at that particular x value. Overall, dv equals pi f of x squared dx. This is a formula worth knowing. You plug that dv into a definite integral, integrate between a and b, where the slabs start and stop, to get the entire volume of the solid. Let's do one more example. Find the volume of the solid generated when the region between y equals tangent x and y equals 0, between x equals 0 and x equals pi over 4 is rotated about the x-axis. So you really should start by sketching that region, like so. I've graphed y equals tangent x, I've graphed y equals 0, x equals 0, and x equals pi over 4 to get a feel for the region that is being described here. I also recommend drawing in one of the rectangles. That way, when we do start thinking about this in 3 dimensions, when we imagine rotating this all about the x-axis, we can picture not just the solid being generated, but also the disk. So here's what all that looks like. When the region is rotated about the x-axis, we get this sort of cone-shaped object. And when the vertical rectangle is rotated about the x-axis, we get a disk. The volume of that disk is going to be pi y squared dx. Here y is tangent x, so we get pi times tangent squared of x dx. We're going to want to integrate that over the full range of x values where we actually get disks. So in this case, from 0 to pi over 4. The volume is going to be given by pi times the integral from 0 to pi over 4 tangent squared x dx. How do we integrate tangent squared? We don't have an anti-differentiation formula for that. Fortunately, there's a trig identity that will help us out. Tangent squared of x is equal to secant squared of x minus 1. That helps us because we do know an antiderivative for secant squared of x. The antiderivative for secant squared of x that we're interested in is tangent of x. And of course, an antiderivative for 1 is just x. I'm going to plug in pi over 4. I'm going to plug in 0 as well, but the tangent of 0 minus 0 is still 0. Evaluate that, remembering that the tangent of pi over 4 is 1. And the decimal approximation for our answer will be 0.67.